So far, we've seen how to describe deformation, right? And we introduced this very important object, the deformation gradient. And from this, we could see that locally we could gain a lot of information about how angles deforms, or lengths, or volumes, areas, and so on. If the deformation is homogeneous, the deformation gradient is constant, and so whatever you find locally is what happens everywhere. If it's inhomogeneous, so in that case, think for instance of torsion. If you do torsion or bending, right? Things. If you're bending a block, yeah, I might bend this block. Oops, like this. Yeah, you can imagine that little elements on this surface are stretched a lot, whereas little elements on the bottom ones are contracted a lot. And so in that case, you need to know what's happening locally rather than everywhere. But if it's homogeneous, like shearing, for instance, everything just tilts together, and all the information you have from the deformation gradient applies everywhere. So that was for deformation. Now we have to ask ourselves, how are we going to create those deformations in the body? And so in this course, we study soft solids that are deformed by forces and moments, or torques. And in this course, in any case, we're on. Oh, sorry, I should bring that a bit further. We're only interested in equilibrium, not in motion. That is not that difficult, but we're just keeping things simple as much as possible. So we're going to assume that the forces and the torques balance out to create equilibrium. Balance out, right? That means 2, 0. It means the resultant is 0. If I sum all the forces, I get 0. If I sum all the torques, I get 0. To create what's called a mechanical equilibrium. And what does that mean mathematically? That's what we want to see today. How are we going to do that? How are we going to describe forces in a body that is soft? All right. If I apply a force, if I apply just a force with one finger, and then I apply the same force, same magnitude of force with the whole palm, surely it's not going to deform the same. And then, since it's soft, things are going to deform inside the body as well, right? Elements are going pushing on others. That seems impossible to describe, and yet it's possible thanks to continuum mechanics, right? So we're going to start with forces. And we're just going to consider two types of forces. You can classify forces in two categories. So it may be subject to, well, the first type is called body forces. And what's meant by that is just that forces that are applied inside, in a way, inside the body, right? So just to give you an example, gravity, it will apply to every particle inside the body. Or electric forces, magnetic force, fields, and so on, electromagnetic forces, etc. So those forces, we won't consider them in this course. So that's nice. Takes care of that part. And the other type of forces that a solid may be subject to are surface forces. Right, just like I was showing you earlier, I apply force on the surface of the body. And then, of course, those surface forces are going to be happening inside, right? If I just look at one part inside of the body, subject to forces from the other side, from the other part of the body, right? And these are the ones we're going to consider in this course. And as I was showing you as well, clearly I could apply the same force depending on how much surface I apply it. You're going to have a deformation. So it's important to talk about surface per unit area. What you must have heard of before is the notion of pressure, right? So we're going to call it T, that's a vector. It's the force per unit area. It's called traction. Okay, so far so good. And then equilibrium. It's just going to read like this. The sum of all the tractions applied on the surface of a solid. I'm only looking at surface forces. And then I'm looking at closed solid. So I'm going to write that circle there just to show it's closed. And then curly D RC. So that's the surface of my body in the current configuration. And if I sum all the forces, it's per unit area, so I need to multiply the traction by the area of a small element and then integrate over the whole surface. So just to show you what it looks like. If I have a body like this, and then I have a little area dA, and then on that surface, there's maybe some tension that's applied. At another point, maybe I have some compression that's applied, and that will be applied on a different dA. You get the idea, right? And I sum all those surface forces over the entire surface of the closed volume, and I get 0. And similarly, I get 0 for the moments. Which, if you remember, is R cross F in first year mechanics, first year applied maths. Now F is TdA because that's the force applied on the small element. Then I need to integrate, but you get the gist. That's equilibrium. Okay, so that wasn't too hard. And then we're going to assume the same thing as Cauchy. And it is that tractions are functions of the position, right? And that's what I've shown here. It changes depending on the position. And of the unit vector, outward unit vector, normal to the surface element. Right, I write it here. And outward unit vector normal to dA. So n, in this case here, it's going to be like this. Here it's going to be like that, right? Your force is not necessarily normal to the area, but that's why I have to define n, the outward unit normal. And then the Cauchy assumption is as follows. T is a function of those two quantities. So T of x, I'm just going to drop it. We just keep it in mind because it's just because I'm lazy. But T of n, we must remember that. And this is very strong. It's stronger than it seems. And it will have consequences, right? The first consequence of this assumption, which is very reasonable, I'll show you now where we're just going to do a thought experiment. So I have my body here, my potato, and I should have done this here. So I'm just going to say consider a body RC. So that's in the current configuration in equilibrium. Yeah, I'm going to call A because RC, that's just too long to write. Its surface area. A. Right, so I need a new page. So my potato here, surface area A, I could, in my mind at least, I could split it in two, right? I imagine that there's a cross section here of area D. And I can see that my body is the same as these two halves. This one, I'm going to call it surface B for the dome, and then D is just the area of the cross section, plus this one here. I'm going to call it C, and there is D as well. Right, you all agree it's the same body. I've separated those two halves, but I can bring them together. And then I'm going to say it's in equilibrium. I'm going to write that 0 is the sum of all the traction on the surface A, the cross surface A. That's right. And it's also the traction on the surface of the top half here, which is B, which is an open surface. Yeah, right then. BA, and it's like this. It's like that. And then there's also D here. That's for the top half. For the bottom half, I have D. Oh, and I should have written N. Right? So if I consider a small surface element, this little blue circle I've done here, I'm going to find it here in the top and here in the bottom. Here, the outward N is going to be this vector. Here, the outward N is going to be this vector. And it's going to be minus N, right? If I bring them together, I get the same normal vector, except one is going up and one is going down. So here I need minus N BA, and then I need to finish with C. All right. And then B and C, I can bring it together. And then if I look at B and C together, I have a closed surface here. In fact, B and C, that's A in surface term. And then I have two integrals of D that I can also bring together. But this here, that's 0. That's why I've written above. And so the conclusion is, since I can do that with any volume in my solid, that T n is minus T minus n. Nice consequence. And we must keep that in mind. It's going to come in handy now. Any questions so far? What have we done? Talked about surface forces, equilibrium of a body with a closed surface, all the traction cancel out. Assume that T depends on N, the outward normal. Now, that has consequence. If you look at your body as a juxtaposition of two halves, then you will have to conclude for this body or for any body that T is an odd function of N, the vector N. Okay, and that's now going to lead you to what's called Cauchy's theorem. Okay,